Now the next part is the connection of quantum electrodynamics to physics, to the rest of physics. And we're going to have a good time now for the rest of the lecture because I'm going to tell you all about the rest of physics. And you can compare the laws of the rest of physics with the laws of quantum electrodynamics. But first I must say immediately that the rest of the laws of physics are not known as well as quantum electrodynamics, and therefore what I have to say is to a varying degrees uncertain. Nowhere near as certain as the electrodynamics. So first there must be a connection because we have to discuss one point. The photon, which couples to the electron, also couples to the nucleus. That's why the electron is attracted to the nucleus. So there's something inside the nucleus that couples with a photon. In other words, we sometimes say it's charged. To say a particle is charged or something is electrically charged is merely a statement that it couples to a photon, that photons are absorbed by it or emitted by it. That's what it means. Anyway, nuclear particles are charged. So in the beginning of the history of this thing, knowing about the nucleus and puddling around looking at them, it became pretty clear that it's easy to understand nuclei of the atoms, that tiny little center where the electrons go around. They're different from atom to atom, and they can all be thought of as being made out of two particles, a number of particles of which, well, how do you say it in English? A group of particles which are either protons or neutrons. Like, for instance, a particular carbon, for example, is a nucleus that has 6 protons and 6 neutrons in it. Nuclei can have, uranium has 146 neutrons and 92 protons in it, and so on. Hydrogen, the simplest nucleus, has just 1 proton in it, and so it goes. So out of protons and neutrons, a nuclei can be made. But the protons and neutrons that are in the nuclei stick together quite tightly. The forces are very large. The energies that are released when you let them jiggle around are much greater in proportion as the atomic bomb is more effective than dynamite. Because the dynamite represents a rearrangement of the electron patterns, and the atomic bomb represents a rearrangement of the proton-neutron patterns. And the relative energies are very large. The particles that interact, when we tried to at first guess would be that the proton is simple also, and that the propagation of a proton, that we make diagrams for protons, same way, and all we have to do is put the mass of a proton in here. Problem, first. It must be that there's more than just photons involved because the forces in nuclei are stronger than electrical forces by about 100 times. If we would invent some new force, we would have to have a kind of a c-square of the order 1, not 137. Because the size of the forces needed are 100 times bigger than electric forces, we call those strong forces. Strong forces are those in which somewhere there's a constant of coupling closer to 1 than it is than electricity. I mean, it might be a quarter, it might be a fifth, it might be 2, but it's not 1%. In investigating this, at the beginning it was hoped that the proton was simple, but the proton kept on showing that it wasn't simple at all. For example, there's many properties that indicate that it's not simple, and the neutron is not simple. For example, the proton, the electron, we talked many times, has a magnetic moment which we can start expanding like this. But the proton has a magnetic moment 279, completely crazy. And the neutron, which is neutral and should have no magnetic moment, no magnetic interaction at all, if it were really neutral, is in fact has a magnetic interaction, which is some number. 3. That indicating that inside the neutron there were some charges that could interact magnetically. It might be neutral, but there are plus and minus or something going around in there, or something. So, to find out more about these particles, which look so much more complicated than the electron, we did many experiments bombarding protons onto nuclei and hitting them harder and harder, first to drive the parts out of the nucleus in order to see how the nuclei were constructed. But in the process, you discover, going higher and higher energies, that you created new particles. And the names of the new particles go, first they discovered pions, and then muons, and then lambdas, and kaons, and sigmas, and x's, and you ran out of the alphabet, so pretty soon it was the sigma 1190 and a sigma 1386 and a lambda 1190 and so on, because you just gave more numbers. And those numbers were the masses of the particles. And ultimately, it is clear that there's an unending number of particles. There being about 400 and some odd particles at the present time, which is it's an open-ended thing. It depends on how carefully you measure. You can't go along with 400 some odd particles. Things get more and more complicated. And then it was realized that these particles can all be understood, cannot all really be understood. We don't know, because now we're moving into partly the unknown. We expect that they all can be understood as being made of others. Now I would like to discuss these others, the so-called, the present guess as to the fundamental particle. Most of the things that are made by bombarding protons and so forth together are supposed to be made of quarks, and I'll tell you about those soon. Those are the strongly interacting particles. But in the process of the experiments, some new particles were discovered which were not strongly interacting with nuclei. The electron, for instance, does not strongly interact with the nucleus. It only interacts through the photon. It's a charge. It's a small thing. It's always got the c squared. There are other particles which do not interact strongly with nuclei. So what I'm going to do is I'm going to divide all the particles up into two classes, those which do not interact strongly and those which do. All right? The ones which do not interact strongly happen to be called by a